So this is the third session on the topic of signals and systems. And in this session, we are going to study the discrete time sine wave. So let us start. What we are going to do is to start with an expression for the analog sine wave, which we have already studied, and then derive the expression for the discrete time sine wave or the digital sine wave. That is what we are going to do. Okay, so let us start, and in the process we shall also study what is digital frequency, what is the interpretation for it. So let us write the expression for the analog signal. Xt is equal to sine of 2 pi f into t. So here x is a continuous variable and t is also a continuous variable. Now we want to make this discrete time. So what we'll do is we'll replace t by n times ts, where ts is the sampling time, as we have seen before. So if we say that sampling time is equal to ts, then t can be replaced by n into ts, where n is an integer. In that case, t will have discrete values, like it may start from 0. So when n is equal to 0, this is 0. When n is equal to 1, this is ts. When n is equal to 2, this is 2ts, and so on. So by using this expression, we convert this continuous time into a discrete time. So then what is the expression we get? So we substitute. So this t is replaced by nts on the left hand side and also on the right hand side. So 2 pi f into t, and t is replaced by n into ts. Now we also recognize that the sampling time period is inversely proportional to the sampling frequency. So what is ts can be written as 1 by fs, and by a slight rearrangement we can write it like this: 2 pi n into f divided by fs. So we have just taken n here, and then ts is 1 by fs, so therefore we can write it in this form. Now it is this ratio of f to sampling frequency. Remember, f is the frequency of the analog signal and fs is the sampling frequency. So this ratio of f to fs we call as our digital frequency. That's the definition of the digital frequency, and we denote it by fd, or the corresponding angular frequency we can write a 2 pi fd is equal to omega d. So the expression becomes sine of omega d into n. Okay, so as I said, the digital frequency is the ratio of the analog frequency divided by the sampling frequency, and since f is in cycles per second and fs is in samples per second, so when you take this ratio, the digital frequency will have units of cycles per sample. Okay. Now there is one unique thing about the digital frequency is that it is limited to a certain value, which is not the case in the case of an analog signal. So let us see that. Now from the sampling theorem tells us that the sampling frequency must be greater than equal to 2 times the frequency of the sine wave. That we had mentioned. We have not yet proved it, but that is the sampling theorem. If this is the case, because unless this is satisfied, you will not be able to recover the signal at the receiving end. That is why this inequality has to be satisfied. Fs has to be greater than equal to 2f. Equal to 2f is of course a theoretical value. In practice, generally it will be somewhat greater than 2f. So if this is the case, if you bring fs on this side and the constant on this side, you can see that the digital frequency has to be less than equal to 0.5. It cannot exceed that. Otherwise, you will not be able to recover the signal properly. So this is a limitation which is unique to digital signal or a discrete time signal, which does not exist for an analog signal. There the frequency theoretically can go right from 0 to infinity, any value. All right. Now this expression that we have got for a given value of fs and f, surely this omega d or fd is fixed. In that case, the parameter that you get in the brackets here is a function of n only. In that case, you can, from the left hand side also, you can simply drop ts and write it as xn. So you can write it as xn is equal to sine of omega d into n, or sine of 2 pi fd into n. That is the expression for the discrete time sinusoidal signal, and we have proved it starting from the expression for the analog signal. Okay, next we want to study the periodicity of the discrete sine wave. That is what we want to study. So let us start. So we got an expression that is sine of 2 pi fd into n. Now suppose we take a value after n samples. So n has some value. Now you add further n samples to this and find out what is the value. So all you have to do is to simply replace n by n plus capital N. That is what you want to do. So this then you can write it as sine of 2 pi fd and n plus n. That is what you can write down. Now you can expand this. So this becomes sine of 2 pi fd into n plus 2 pi fd multiplied by n. Now notice that this product of fd multiplied by n, if it is an integer, then the angle is changed by an integer multiple of 2 pi. And if that happens, the sine value is retained. That is, whatever is the value of this sine function will be same as the value of this function, assuming that the product of fd into n is an integer. So that is the condition. So if fd into n is equal to k, where k is an integer, then this is equal to this. And in that case, fd we have already, so in this case you can see fd, what is fd? That was previously we had defined it as f divided by fs, but now in terms of k and n also we get fd. So actually fd can be defined in two ways. It's a ratio of k by n, where k is an integer and n is the number of samples after which the sine wave repeats. Okay, and it's also equal to f by fs. All right. So how do you find this time period? That is the value of n. N is the number of samples after which the discrete time sine wave repeats. So we want to find out what is the value of this n. So suppose f is equal to 30. This is the frequency of the analog sine wave, and you sample it, let us say, at 70 samples per second. In that case, k by n, which is same as f by fs, is equal to 30 by 70. So this n corresponds to 70. However, note that we are interested in finding out the minimum value of the n after which the sine wave repeats. That is always the case for finding the time period, because sine wave will repeat for so many samples. So it will repeat for minimum value of n, then increase it 2 times, again it will repeat, and so on. So what you have to do is to remove the common factors from this ratio. So to find the period, remove the common factors from the numerator and the denominator. So you get k by n, that is 30 by 70, that is 3 by 7. So this 0 cancels here, and you get 3 by 7. So after doing all this, what have we found out? We have found out that if my original sine wave has a frequency of 30 Hertz, and if I sample it at 70 samples per second, then the discrete sine wave that I get repeats after 7 samples. That is what it means. So after 7 samples, one cycle of discrete signal is complete. Okay. Note incidentally that when we talk about the time period of an analog signal, time is a continuous variable. So we talk in terms of capital T, which is in terms of seconds, maybe 0.1 second, 0.2, and so on. But in a discrete sine wave, your time period is in number of samples, because your n is an integer, that is, the independent variable is an integer now. So for this particular example, we have found out that the capital N is equal to 7. After 7 samples, one cycle of discrete signal is complete. And if f and fs are different, you can of course follow the same procedure in order to find n. Of course, just remember that your fs has to be at least 2 times f, and in fact slightly greater. So in this case, you can see if this is 30, 2 times f is 60, and I have chosen a sampling frequency which is 70, which is greater than 2 times f. All right. Then another thing we want to find is the relation between analog period and the digital period. So let us proceed. Fd, as we know, is given by k by n. We also know that it is given by f by s. Now f is 1 by t and fs is 1 by ts. So we can write it like this: ts divided by t, that's equal to k by n. So by cross multiplication, we can write this equation: n into ts is equal to k times t. What does it mean? Now n is the number of samples after which the discrete sine wave repeats. So n into ts. Now ts is the sampling time period. So this is the total time taken by one cycle of the discrete sine wave. On the other hand, if you look at this t is the time period of the analog sine wave and k is an integer. So this will tell you, so if t is multiplied by k, it means that during this time period, k cycles of the analog sine wave complete. So let me repeat that. Time of n samples, one cycle of discrete sine wave corresponds to k cycles of the analog sine wave. Okay. Alright, so now what we are going to do is to study a couple of programs. The first one in which how to generate and plot the discrete sine wave, and the second in which we shall try to prove that equation. We shall show that equation that your n multiplied by ts is equal to k times t. These couple of programs we will study. Okay, so as usual, your clear console, clear the variables, clear the figure. A equal to 1, that is the amplitude of the sine wave. This could be different. Then let's say k is given to us and n is given to us. So I am using the same example that we had worked out just now. So k equal to 3, n equal to 7. Now n is a variable. Remember, it's a discrete variable and we are assuming that it starts from 0 and goes up to 21. So the default increment is 1. That's why it need not be written here. Remember, this generates an array. So what it will do, n1 will be equal to 0, n2 will be equal to 1, n3 will be equal to 2, and so on until you reach the value of n which is equal to 21. Now since we have taken 21 samples for plotting, and since after 7 samples the discrete sine wave repeats, we expect to see 3 cycles of the discrete sine wave, and we shall verify that. Alright, so now you generate your signal. This is again a vector, because remember, n is a one-dimensional array or a vector. So for each value of n, there will be a value of x generated, and the number of samples in x, of course, will be equal to the number of values in n. Then you can plot it. Now you make a stem plot. So usually when you are plotting an analog signal or a continuous time signal, you use the plot function. Okay, so that gives you a continuous graph for the analog signal. But when you are talking about discrete signals, remember, your independent variable is a discrete value n, so it can be 0, 1, 2, and so on. So it is more convenient to make a stem plot, so, or a line plot. And for making the line plot, the function in the MATLAB is stem. So we use that. Stem nx, line width we have already discussed. You can use 2, 3, 1 or whatever. Grid on. Then x label. So on the x-axis you have the sample index, that is n. Font size we take 16. Y label, amplitude x, font size 16. Remember, the amplitude is still a floating point variable, because remember, all signals and systems theory is developed assuming that your time is either continuous or discrete, and amplitude is always assumed to be continuous. Okay, that we have discussed before. All right, so now once you have entered this program and you run it, this is what you will get. So you get a line plot, and you can see here, this is the first sample. So 1, 2, 3, 4, 5, 6, 7, and then it repeats again. It started from 0 you see exactly same pattern is repeated. So again 1, 2, 3, 4, 5, 6, 7, and again repeated. So 1, 2, 3, 4, 5, 6, 7, and this is where the next wave starts. Notice the difference between the discrete sine wave and the continuous. For the continuous, where one cycle ends, the other starts. Whereas in this case, you will find that it ends here but starts a little later. However, the time calculation is still okay. That is still going to be n multiplied by ts, because you see this, the gap, time gap here, this 1, 2, 3, 4, 5, 6, and then you need one more 7. So this time period in terms of time is still going to be n into ts. So we have plotted like this. All right, so I hope this is clear. On the x-axis you have sample index n, and on the y-axis you have amplitude, which is of course a floating point variable. All right. Then we want to write a program in which we are going to demonstrate that n into ts is k times t. So first we shall study the technique, how to do it, and then we'll look at the program. So suppose f is equal to 30, fs is equal to 70 as before. In that case, the sampling time is 1 by 70. Okay, that is a reciprocal of the fs. Now k by n is 3 by 7. So n is equal to 7. So which means the time taken for one cycle of discrete signal is n into ts, that is equal to 7 into 1 by 70. Remember, ts is 1 by 70. That is equal to 0.1 second. So the point is, one cycle is taking 0.1 second. So if you generate an analog signal of frequency 30 Hertz and keep the total duration of 0.1 seconds, you should see 3 cycles. Understand, when you are generating the analog signal, the sampling frequency that you are using has nothing to do with this sampling frequency. That is simply a sampling frequency chosen to simulate the continuous time signal. So don't be worried about that. So that sampling frequency can be anything. But the point is, if you plot the sine wave for the duration of 0.1 second, you should see 3 cycles. That is going to demonstrate this equation n ts is equal to k times t. So in the MATLAB program, we generate discrete signal over one cycle, 7 samples, and plot n ts versus x. Normally, that is discrete signal, the independent variable is only n, but since we want to show this particular equation, that's why we are plotting n into ts. So the x-axis will be calibrated in terms of time. Okay, it will still have discrete values, but calibrated in terms of time. So you plot this versus x. Then what you do, then you generate and plot sine wave of 30 Hertz over 0.1 second and verify that over 0.1 second analog signal completes 3 cycles. So this is the general technique. So given f and fs, this is how you proceed. So I have taken one example, but you could change this and verify this for other values as well. Okay, so let's look at the program now. So this is usual CLC, clear, CLF, A equal to 1, F equal to 30, Fs equal to 70, Ts is 1 by Fs, K equal to 3, N equal to 7, N is 0 to 7 with an increment of 1, which is the default increment. Then calculate X. Then what you do when you are plotting on the x-axis, instead of just plotting n, we are plotting n into ts. Remember, we wanted to verify that particular equation. That is why we are doing it. The rest of the things are similar. So x label, y label, title, etc. So this part of the program generates the discrete sine wave and plots it. But we also want to compare it with the analog sine wave or the continuous time sine wave. So let's see the next part of the program. So now we choose some sampling frequency for plotting the analog signal. Note that this sampling frequency has nothing to do with the sampling frequency that was used to generate the discrete sine wave. This is just for plotting the analog sine wave. Okay. So TSA will be 1 by FSA. So now you generate your T vector 0 TSA, but now this is the point. So we had plotted that over 0.1 second and we plot this also over 0.1 second. But in this case you will find that the analog signal will complete 3 cycles, whereas the discrete signal will complete only 1 cycle. So XA, amplitude of the analog signal, 2 pi ft, subplot 212. So plot, first you plot the analog signal, okay, gray dawn, etc. Then get the plot for the discrete sine wave as well as the continuous time sine wave. And look at this now. So since this is NTS, this is calibrated in terms of seconds. So 0 and goes up to 0.1 second. And you can see it completes 1 cycle. So 1, 2, 3, 4, 5, 6, 7 and repeat is 0.1 second. And for the continuous time sine wave, we are plotting this. So this is 0. So we have plotted it over 0.1 seconds and we see that this is 1 cycle, these 2 cycle and these 3 cycle. So we have shown that 1 cycle of the discrete sine wave takes time which is same as the time taken by the 3 samples of the sine wave for this particular example. And that's all in this particular session.